All right, one more video I want to add into this section. It kind of scratches the surface of a topic that once you learn opens up this whole new world and is super interesting, but we're not going to get into all that. I just want to kind of briefly introduce this idea of complex roots. So what am I talking about when I talk about a complex root? Well, think about this function, y or f of x equals x plus 3 squared plus 4. It's a polynomial, although it's written in kind of a weird form, a form that we referred to as vertex form a few sections ago, that allow us to come up with the graph by applying function transformations. So the idea is we start out with our standard parabola that has a vertex at 0, 0, but then this positive 3 right here causes us to shift the graph left 3 units. And this positive 4 causes us to shift the graph up 4 units. So instead of the vertex being here, we have to move it left 3, up 4, it ends up right around in here. And then because of the implied 1 out in front here, we don't have to do any stretching or flipping or anything like that. So we can just kind of sketch our standard parabola from here. And maybe we come up with a graph that looks more or less like this. Really, it doesn't matter too much what the graph looks like. The point is just, if we're thinking about the roots of this polynomial, so far our interpretation of that is just the x-intercepts, the points at which this curve cross our x-axis here. But there's a problem with this specific graph. It clearly never is going to cross our x-axis, so it doesn't have any x-intercepts. And up until this point in the class, that meant it didn't have any roots. But now what we're going to do is change things a little bit so we can refer to its roots. And you're like, wait, I thought it didn't have any roots. It doesn't have any real roots. But if we change our definition of what we allow to be a root to include things that are called complex roots, then polynomials such as this that don't have any x-intercepts can still have roots. Those roots just won't correspond with real numbers. And maybe you're like, whoa, wait, what, real numbers? I didn't know that there were numbers that weren't real. Well, there's a whole nother system of numbers called complex numbers that are super interesting, and I could spend hours talking about it, but I'm not going to. For the purposes of our class, all you need to know about complex numbers is they're going to be in the form a plus bi, where a and b are real numbers, and I is a symbol that we use to represent the square root of -1. So for example, -3 minus 2i is a perfectly good complex number. 1/2 plus 0.3i is a perfectly good complex number. I is a perfectly good complex number because that's of this form, with the a being a 0 and the b being a 1. These are all examples of complex numbers. And when you learn how they work, they unlock this whole new world in math where numbers become two-dimensional instead of one-dimensional. And again, it's super interesting, but we're not going to talk about it in this video. In this video, I just want you to know that we could have the same question we've been asking, trying to find roots of a polynomial, but sometimes those roots won't all be real numbers, like in this case right here. And I still want to be able to answer the question, so this is how we're going to answer it. First comment. Typically, polynomials are not given in this form, right? A more common form for you to see this written would be if I expand these parentheses, I get x squared plus 6x plus 9, and then I have this plus 4. So this polynomial would be y equals x squared plus 6x plus 13. So maybe think about this as the starting point, as opposed to this up here, which is what we used to figure out what the graph of this polynomial looks like. So if you started here and you're trying to figure out the roots, what would you do? Well, it's tempting to use the methods of this section and look for all the possible rational roots by taking the factors of 13 and dividing it by the factors of 1. The problem is that only gives you the rational roots, and complex numbers are not rational numbers, so that method will not give you any of the complex roots. Fortunately, this is just a second-degree polynomial, so we don't need to do that trick. We can just solve it directly. To figure out the complex roots of a second-degree polynomial, all we have to do is take that polynomial, x squared plus 6x plus 13, and set it equal to 0. Think about what we're doing right here. We're making the y value equal to 0. We're looking for when this graph has a y coordinate of 0. And you're like, that's not going to happen. I can see clearly from this graph that that's never going to happen. That's not true. This graph only shows you the real numbers. It doesn't show you the complex numbers. Interestingly, to see the inputs and outputs of this polynomial, if we were allowing complex inputs and outputs, we'd need 4 dimensions. So we couldn't even draw the graph. It gets super wild. But again, I'm trying to keep myself on topic. How do you solve this equation? Well, you got 3 options. The same 3 options that we've seen so far in this class. You can try to factor this thing, you can use the quadratic formula, or you can complete the square. Personally, I'd probably complete the square. I'd subtract 13 from both sides of the equation to get x squared plus 6x equals -13. And then I'd be like, I don't have a perfect square over on this side of the equation, but if I had let's see, half of 6 is 3 and 3 squared is 9 right here, then I would have a perfect square. So I'm going to add 9 to both sides of the equation. That leaves me with the perfect square on the left-hand side. Specifically, it leaves me with x plus 3 squared. And over on the right-hand side, I got negative 4. Essentially, what we're doing with this method is we're kind of undoing the steps that we did right here. Maybe you can kind of see parts of this over here. Anyways, our goal is to get the x all by itself. So at this stage, I take the square root of both sides of the equation, and I get x plus 3 equals, make sure when you take the square root, you put in the plus or minus, the square root of negative 4. And you're like, yeah, I knew all that, but this is where I get stuck. You can't take the square root of negative 4. And I'd be like, yeah, you used to not be able to, but now you can. Now that we're allowing complex numbers, you can take the square root of negative 4. Here's how you do it. The square root of negative 4 is the exact same as the square root of positive 4 times the square root of negative 1. This is one of our exponent rules that allows us to write this way. The square root of 4 is just the number 2, and the square root of negative 1, we're defining that to be equal to I. So because the square root of negative 1 is just equal to I can change the square root of negative 1 into an I. I got x plus 3 equals plus or minus 2I. I got x equals negative 3 plus or minus 2I. What I'm saying is there's two solutions to this equation right here. This polynomial has two different roots or zeros. They're just not real numbers, they're complex numbers. One of them is negative 3 plus 2I. The other one is negative 3 minus 2I. They don't show up on this graph, but they're the solutions to this problem. A couple of comments here. First off, you might notice that these are very similar, right? They both have a negative 3 in place of the A, and one has a positive 2 in place of the B, and the other has a negative 2 in place of the B. They're almost the same complex number. The only difference is the sign in between the A and the B. When you have two complex numbers that fit that form, that have the exact same value of A and opposite values of B, they're what are called complex conjugates. And maybe you can see by the method that we use to solve here that complex roots are always going to come in conjugate pairs. What that means is if you somehow knew that negative 3 plus 2I was a complex root for this polynomial, then negative 3 minus 2I would have to be a complex root of this polynomial. Another comment that I want to make is we solved this equation by completing the square. You also could have solved this equation by using the quadratic formula. And maybe that's a good exercise for you to do. Make sure that you can get the exact same answers using the quadratic formula. It's not super interesting, but you can do it. You can also solve this equation by factoring. I don't recommend that you do this, but I want to show you how it still works out. It's kind of interesting. If I had x squared plus 6x plus 13 equals 0, I could say, all right, this is a quadratic trinomial. So when it factors, it's going to factor into two different binomials. And because my leading coefficient is a 1, I have 1x here and 1x here. And then all I have to do is look for two numbers that I'm going to write here and here that when I multiply them together give me 13, and when I add them together I get 6. And you'll think about that for a really long time and you'll be like, let's see, to multiply to 13, 1 and 13, but those can't add to 6. Negative 1, negative 13, that can't add to 6. Oh, maybe there's like some fractions in there or something. No, the reason you're having such a hard time finding the two numbers that you put in this spot and this spot is those two numbers are not real numbers. Those numbers are complex numbers. Those numbers are 3 plus 2i and 3 minus 2i. Right? Try it. Add these two things together. 3 plus 2i plus 3 minus 2i. Let's see, 3 and 3 gives me 6, and 2i and negative 2i gives me 0i. In other words, 0. When I add these two things together, I sure do end up with 6, the coefficient on my linear term. And when I multiply these two guys together, I'd have to think FOIL. 3 times 3 would give me 9. 3 times negative 2i would give me negative 6i. 3 times positive 2i gives me positive 6i. And 2i times negative 2i. Let's see, a positive times a negative is a negative. And 2i times 2i would be 4i squared. The negative 6i and the positive 6i cancel out, so I got 9 minus 4i squared. I thought you said this was supposed to be 13. This is 13 because I squared equals negative 1. Wait, why does I squared equal negative 1? Because I equals the square root of negative 1. So if you square both sides of this equation, you get that I squared equals negative 1. So this is 9 minus 4 times negative 1. This is 9 plus 4. This is 13. When you add these two numbers together, you do get 6. And when you multiply these two numbers together, you do get 13. This problem does work by factoring. The problem is you have to think in terms of complex numbers. And nobody realistically can do that, right? Nobody's going to be thinking of complex numbers. Nobody's going to be able to come up with 3 plus 2y and 3 minus 2y as the two numbers that add to 6 and multiply to 13. So that's why it's not a great idea to solve these problems by factoring. But I did want to make the point that it works. You can solve these problems by factoring, right? If I were solving this by factoring, I now have something times something equals 0. So either x plus 3 plus 2i is equal to 0, or x plus 3 minus 2i is equal to 0. I'll subtract this 3 plus 2i thing over to this side of the equation, and then maybe I'll get rid of the parentheses by taking the negative and distributing it through, and I get x equals negative 3 minus 2i as one of my roots. Same idea over here. I'll subtract it to the other side of the equation and get x equals negative 3 minus 2i, and then distribute the negative through the parentheses and get x equals negative 3 plus 2i as my other root. The exact same roots that I came up with here, negative 3 plus 2i, negative 3 minus 2i, I can come up with by factoring if I can factor over complex numbers, which realistically nobody can. You're like, all right, so if I'm not going to be able to do this, why are you showing me this method? It's useful to be able to start out with the roots, complex roots, and recreate the polynomial. Maybe I'll demonstrate that in a second example down here. What if I was asked to find all the roots of this polynomial, x cubed minus 7x squared plus 25x minus 39? Well, I could list all of the possible rational roots by taking the factors of 39. So what's that? 1, 3, 13, and 39. And dividing those by the factors of 1, I get plus or minus 1, 3, 13, and 39 as my possible roots. You play with those for a little while, maybe with the help of a calculator, and what you see is, if we call this polynomial f of x, f of 3 ends up being equal to 0. F of 3 would be 3 cubed minus 7 times 3 squared plus 25 times 3 minus 39. And since 3 cubed is 27, and 3 squared is 9, and 9 times 7 is 63, and 25 times 3 is 75, and I still have this negative 39, I can look at the sum of my positives, the 27 and the 75, and I think I end up with 102. And then I can look at the sum of my negatives, negative 63 and negative 39, and that's negative 102. So when I take the 102 minus the 102, I end up with 0. I don't need you to be able to do all that arithmetic. I think on the homework I say something like, hint, the only real root happens at x equals 3. Or on a quiz I might say, check that 3 really is a root of this polynomial, and you can go through these steps. The point is, I don't want you to just search for these roots, but I do want you to know in theory how you come up with a finite list of the possibilities for these rational roots. We found one of them. Where do we go from here? Well, we can use all the methods that we learned in this section, right? If 3 is a root, then x minus 3 is a factor. And if x minus 3 is a factor, I can use polynomial long division to start factoring this polynomial. To get rid of this x cubed, I throw an x squared up top. X squared times x minus 3 gives me x cubed minus 3x squared. And then I have to subtract all of this stuff. X cubed minus x cubed goes away. Negative 7x squared minus negative 3x squared is the same as negative 7x squared plus 3x squared, which is negative 4x squared. And then I bring down the 25x. Now my goal is to get rid of this negative 4x squared. So I'll toss a negative 4x up here and then multiply that negative 4x times the x minus 3. That product is negative 4x squared plus 12x. And then I'm going to subtract again. Negative 4x squared minus negative 4x squared goes away. 25x minus 12x leaves me with 13x, and I bring down the negative 39. To get rid of this 13x, I'm going to have to put a 13 up here. And when I multiply this 13 times x minus 3, I get 13x minus 39, which is awesome because when I subtract that from this 13x minus 39, I get a remainder of 0. What that tells me is my polynomial f of x, which was originally given to me as x cubed minus 7x squared plus 25x minus 39, can be rewritten as x minus 3, the factor that I came up with after I recognized that 3 was a root, times this quotient x squared minus 4x plus 13. I know one of the roots, 3, that corresponds with this factor. I don't know the two roots that correspond with this factor, but I can find them. All I have to do is solve the equation x squared minus 4x plus 13 equals 0. 3 options in terms of how I solve this, right? Complete the square, factor, or use the quadratic formula. I wouldn't recommend factoring. And since that's normally our go-to method, if this were like a test or something, maybe I'd tell you that this polynomial contains complex roots, so you'd know not to factor at this step. I think your best bet is to complete this square. To subtract 13 from both sides of the equation, so you got x squared minus 4x equals negative 13. And then figure out what number you can add to both sides of the equation to leave you with the perfect square over here on the left side. In this case, that number is positive 4, because half of this negative 4 is negative 2, and negative 2 squared gives me this positive 4. What I now have is a perfect square on this side of the equation. So I got x minus 2 squared is equal to negative 9, the sum of the negative 13 and the positive 4. And now I can solve this equation. Take the square root of both sides of the equation, make sure you put in the plus or minus. I got x minus 2 equals plus or minus the square root of negative 9. Uh-oh, that's a problem. No, it's not. It used to be, but it's not anymore. We can just view the square root of negative 9 as the square root of 9 times the square root of negative 1. X minus 2 is equal to plus or minus 3, the square root of 9, times I, the square root of negative 1. If I add 2 to both sides of the equation, I get x equals 2 plus or minus 3i. In other words, my complex roots are at x equals 2 plus 3i and 2 minus 3i. And from above, I figured out that I have a real root at 3. So this third degree polynomial has these 3 roots. 1 real, 2 complex. Last thing I want to show you before I call this good is I want to undo all this work. Suppose you had a polynomial that has these 3 roots. And since you can always multiply polynomials by constants without changing their roots, I also have to specify that maybe the leading coefficient is just 1. So supposing you have such a polynomial, can you find its equation? And the answer is absolutely you can. What you would do is be like, if 2 plus 3i is a root, x minus 2 plus 3i must be a factor. And if 2 minus 3i is a root, x minus 2 minus 3i is a factor. Be really careful with your parentheses. And if 3 is a root, x minus 3 is a factor. So my polynomial must be the product of those things, and there might be some constant term out in front. I'll represent that constant term with an a, and I'll solve for that later. When you're asked to find a polynomial, typically you want the polynomial written in its unfactored form, or at least without any complex numbers floating around in here. So what you have to do is expand all of this, multiply this times this. That looks really intimidating, but it's not as bad as maybe you'd think. So I'm going to leave this x minus 3i completely alone, and my goal will just be to multiply together these 2 factors. I know from experience that that's going to get really ugly, so I'm going to leave myself a ton of room and take this product and write it in these parentheses. So what do I get when I multiply this times this? Well, the trick is to think FOIL. See this as 2 terms. One of the term is the x, and the other term is this 2 plus 3i, and there's a negative sign in between those 2 terms. And view this as 2 terms. There's an x, and then there's a 2 minus 3i. And in between those 2 terms is a negative sign. So if I'm thinking FOIL on those 2 sets with 2 terms in each, I first have to take this x times this x to get x squared. And then I have to take this x times this negative 2 minus 3i. Rather than do any crazy distributing here, notice that it's a negative times a positive, so it's going to be negative. And then I have whatever x times 2 minus 3i is equal to. I'll figure that out in the next step. I guess that would be the O in FOIL, the outside terms. So now I want to do the I in FOIL, the inside terms. I again have a negative times this x, so I get negative x times this 2 plus 3i. Finally, the L in FOIL is the product of these 2 guys. Well, it's a negative times a negative, so I'm going to get a positive. And then what is that product? Well, I'll figure it out in the next step. For now, I'll just write it's whatever 2 plus 3i times 2 minus 3i is equal to. The way to think about it is we've gotten rid of these parentheses, but we still had some parentheses inside here, which leave us with some parentheses inside this outer set of parentheses. But now we can get rid of this next layer of parentheses. I'll bring the x squared straight down. I'll get rid of these parentheses by taking the negative x and distributing it through. So I get negative 2x plus 3ix. Then I'll take this negative x and distribute it through these parentheses. So I get negative 2x minus 3ix. And then finally, I'll get rid of these parentheses by doing FOIL one more time on these 2 binomials. This 2 times this 2 gives me a 4. This 2 times this negative 3i gives me negative 6i. This 3i times this 2 gives me positive 6i. And then this 3i times this negative 3i, well, positive times a negative is negative. 3 times 3 gives me 9, and I times I gives me I squared. Don't forget, we still have this x minus 3 to deal with later. This looks terrible. This looks really hard to deal with, but it's going to get significantly nicer in the next step. We'll leave the a alone, and we'll work on these same sets of parentheses. Let's see, I got an x squared term. I can write that here. I got negative 2x and then another negative 2x. So in total, I have negative 4x. I have this 3ix, but I also have this negative 3ix. So those guys are going to cancel out. Similarly, I have this 6i, but I also have this negative 6i. So those guys are going to cancel out. I've got this 4 and this negative 9i squared left over. But remember, negative 9i squared is the same as positive 9 because I squared is the same as negative 1 because I is the square root of negative 1. So if you square both sides, you get that I squared equals negative 1. What that means is when I'm trying to find the sum of 4 and negative 9i squared, I'm really just trying to find the sum of 4 and positive 9, which is just the number 13. What I'm saying is my polynomial all of a sudden can be written without any complex numbers at all. X squared minus 4x plus 13 times x minus 3. We still don't know if there's a number out in front, so we still have this a. Our hint to figuring out a is that the leading coefficient is just equal to 1. Can't quite see the leading coefficient yet, so maybe I'll expand this polynomial. I'll take this x and multiply it by each of these three terms. And then I'll take this negative 3 and multiply it by each of these three terms. So the x times the x squared gives me x cubed. The x times the negative 4x gives me negative 4x squared. And the x times the 13 gives me 13x. And then the negative 3 times the x squared gives me negative 3x squared. And the negative 3 times the negative 4x gives me positive 12x. And the negative 3 times the 13 gives me negative 39. Finally, if I collect like terms, I got x cubed. For my x squared terms, I got negative 4 and negative 3 of them. So I got negative 7x squareds. For my x terms, I got 13 of them and 12 more of them. So I got 25 of these x's. And then finally, for my constant term, I got negative 39. Since I'm told that the leading coefficient is equal to 1, this value of a must be equal to 1, and my polynomial f of x must be equal to x cubed minus 7x squared plus 25x minus 39. Oh, right, that's what we started out with way up here so long ago. This is the polynomial that has roots 2 plus 3i, 2 minus 3i, and 3, and a leading coefficient of 1. Note the leading coefficient is 1 here, and we figured out the roots, and those were exactly what we came up with. The point was supposed to show how you can go in both directions, although this working backwards idea can be really miserable, especially in these steps in here. But at least now you have an outline of how to do it.